Hello everyone. In today's session, I am going to discuss the concept of weighted graph and we'll discuss the concept of Dijkstra's algorithm 2, which is used to find the shortest path in a weighted graph. So let us see that what exactly we mean by a weighted graph. So a weighted graph is a type of graph in which each edge of the graph is assigned some numerical weights. When I'm saying numerical weights or numerical value, it means what these weights can be considered as the quantity associated to an edge. It may be like distance, it may be like cost, it may be capacity, or it may be any other relevant matrix depending on the context of the problem. So, like it may gives you the distance from traveling one point to point A to point B, and that distance is assigned to that edge as a weight. It may be the cost of traveling from point A to point B. It may be the time or it may be any other relevant matrix. So this is how we can define a weighted graph. So like commonly or in most of the time when a weighted graph is there, we can connect it with the real application or real life based problem like land problem, network design, route planning, optimization, shortest path, spanning tree, Google Maps, Net. Google Maps can be considered as one of the best examples of the weighted graph. Like when we ordered the food through Swiggy or Zomato's, we can see that a tentative time shows that till this time you get your delivery. So how they predict this? The concept is term concept is taken from the weighted graph, and on the basis of the weighted graph, what they did, they used the algorithm to find the optimal path so that your order is delivered within the less or the least possible time as per the restriction. When we book our taxi through Ola, Uber, a tentative time is shown that how much time you are supposed to take from point A to point B. A tentative cost is also there. Okay, so if in place of time it is associated with the cost, a minimum or we can say optimal cost can also be calculated on the basis of the weighted graph. Okay, so now you can see over here there are few weighted graph shown, few of the weighted graph shown. Like the first graph shows the mileage from this point A to this point B is 2534. So yes, this is also an example of weighted graph where in place of distance, time or cost, a mileage is shown. The second graph shows the traveling cost, the fare from point A to point B or from any between any 2 points. So if anyone want to travel, let it be from Los Angeles to Miami, there are certain path exist and we are supposed to choose which one gives you or which one allow you to travel from Los Angeles to Miami in the least cost. The third graph, it shows the time. So like one more example of the weighted graph in terms of the time unit. So these are the few more example in terms of distance, in terms of the response time, in terms of the lease rate per month. So these are the few of the example of the weighted graph, and these graph can be solved, or better to say, can be used to find the optimal solution for the given problem in whatever context the problem is modeled. There are various methods, or better to say, various algorithm exist to solve such problem. And one of the contexts for such problem is what to find the shortest path. Shortest path, it may we can find the shortest cost, the shortest traveling time as per the nature of the given problem. Now, what exactly we mean by shortest path, as it is a common term and most of us already know it, The shortest path problem means it is a process to involving the shortest way to move out from point A to a vertex A to a vertex B, where each edge is given some weight. This concept is only for the weighted graph, so that's why we are writing it in terms of weighted graph. If a graph is not weighted, then in that case, few of the problem, what they did, shortest path means the minimum number of edges they do have. Okay. Now, as already discussed, shortest path, what exactly it means what? The shortest path, when I'm talking about shortest path, it is also associated a term which is shortest distance. So a path may be any sequence of vertices and edges as we already know it. Now the shortest distance is what? The sum of the edges that are present in the shortest path is called as the shortest distance. If it is in terms of distance, it called as the shortest smallest cost. If it is that the graph is given in terms of the cost. Okay, so these are few of the way in which we can understand what exactly a shortest path problem means. There are several algorithms that we do have for finding the shortest path, like we do have Floyd-Russell algorithm is there, Dijkstra is there, Prim's is there, and many more. In today's session, I am going to explain the concept of the Dijkstra's algorithm to find the shortest path in a given weighted graph. In a given weighted graph, the Dijkstra's algorithm is based on certain, what should I say, certain prerequisite. Like one of the prerequisite is that the weighted graph must have the weight of each edge as a non-negative number. If the edges is having the weight as a negative number, then this algorithm can't be used to find the shortest path. So this is one of the restriction for this one, this Dijkstra's algorithm. One more thing is what it is used to find the shortest path from source to destination. It's not that it will give you the shortest path between every possible pair of the given graph. If you change the source and destination, you are supposed to implement the algorithm in one more time to get exactly the shortest path. Okay, so this is what some basic about the Dijkstra's algorithm. Now, let us take one example or one problem that how we can solve this problem by using the Dijkstra's algorithm. So over here, we can see that we do have the five vertices a, B, C are the labeling or the naming is given for these vertices. The distance is given as 5, 7, and the other units are other between other edges, the distance are given. And as per the nature of the problem, we are supposed to find the shortest distance from the vertex A to vertex E. Okay, now, most of the like books is solving digest problem based on Dijkstra algorithm by making matrix. But over here, we'll try to solve it in a little different manner, not exactly in terms of matrix, but it is replicating the entries of a matrix. Okay. So now, over here, let us see that how exactly we can solve this problem by using the Dijkstra's algorithm. So let us try to solve this problem. And as it is given that we are supposed to find the shortest path from A to E. So first we'll give the shortest path and also along with the shortest path, we'll give the shortest distance too. Because the ultimate motto or ultimate like assignment for finding the shortest path means we are interested to find the shortest distance too. Okay, so we should start from the vertex A. Let us see how we can solve it. So we are starting from the vertex A, the step number one for this algorithm. Now we will see that how many ways are there to move out from vertex A. From this graph, we can say we can move out from A by using the edge which is given A to B, or we can move out by using edge which is given A to D. A to B, it is given as distance 5 and A to D given distance 2. So if we are using the first one, we are supposed to travel 5 units. And if it is A to D, we are supposed to travel 2 units of distance. Okay. So this is the first part. Now, what we are supposed to do, we are supposed to select the minimum out of these two. It is 5, it is 2. So out of 5 and 2, whatever is the minimum, we are supposed to select it. So let us select 2 because 2 is the minimum out of 5 and 2. It means the next selection after A is D. So now we are on the vertex D with a weight of 2. Weight of 2 means we traveled the 2 units distance. Now at the point D, how to move out? We do have ways to move out from D. We can move out through B, in which we are supposed to travel 4 unit, and from D to E, where we are supposed to travel 8 unit distance. So if I take D to B, the total will be, that means 2 plus 4, so it comes out as 6 unit, and over here it is 2 plus 8, so comes out as 10 unit. Now we'll repeat the last step in which we are supposed to select the minimum. Over here, there's a one point that we should pay attention. That is what we are supposed to select the minimum from all unselected. So all unselected means what? 5 is not selected till now, 6 is not selected till now, 10 is not selected till now. So it's not that on the current step we are selecting the minimum. It says that from all the previous, including the current one, we are supposed to select minimum from unselected, from unselected weights. Okay. So now the minimum is 5. So I will select this 5. I will select this 5. One more point that you need to take care in this process is what? When you select a vertex with a minimum weight, and if that vertex is present on some other selections too, on some other steps too, then that vertex get cancelled out. That vertex get cancelled out. Like I'm selecting B with a weight of 5, and over here you can see B is also existing with a weight of 6. So this got crossed. It is very important to cross with the of the vertex which is the same name but having the higher weight. Okay. So in step number 3, we are on the vertex B with a weight of 5. With a weight of 5. Now let us see that what are the ways to move out from the vertex B. So from that graph, we can see that from B, we can move to C by traveling 7 unit of distance, and B to E by traveling 4 units of distance. So it will make total as 5 plus 7, that means 12. And this is 5 plus 4, that means 9. It's not the current weight, do include the previous weight too. Okay, now once again, we are supposed to revise the step, the previous step where we are supposed to do the selection of the least weight from all unselected and uncrossed. Okay, because few of the weight get crossed also. So now unselected, this 10 is unselected, this 12 is unselected, and this 9 is unselected. Rest all of them either selected or crossed. So minimum out of these is 9. So I will select this 9, which is E. So parallelly, I will cross those E where the weight is more than 9. So this get crossed because we are selecting E with the weight of 9. So over here, this E is having weight 10, so it get crossed. The same name vertices get crossed. Huh? It's not all other vertices get crossed. So now in the next step, we are on the vertex E with the weight, how much? 9 unit selection, 9 unit of distance. And 9 unit, our destination point is also E. Our destination point is also E. So we arrived at the E vertex. The task is done. But the thing is that the algorithm will not stop. The algorithm will not stop until unless all the vertices, not in the graph, all the vertices means what? Here, those vertices are listed, either crossed or non-selected. Either crossed or non-selected. So just see the first one, yes, it is selected. This is selected. So this is selected, this got crossed, this got crossed. This vertex C neither selected nor crossed. So will not, the algorithm will not terminate over here. We need to do one more selection. So over here we have selected E. We will not write E and then check the further path because we are supposed to arrive at E. Okay, but still C is open. So now let us select C with a weight of 12. So C will be selected with a weight of 12. Okay, now what are the paths to move out from C? From C, there's a vertex which is connected to B, but B is already visited, so we can't visit it again. A vertex once selected will not supposed to be visit again. C to E, you can see E is already selected. So from C, there is no further path. From C, there is no further path, so we will cross it. Now you can see every vertex which is present in these steps is either crossed or selected. So the algorithm is terminated. So algorithm is over. Now, how to write the shortest path? How to write the shortest path? Let us try to see. So for writing the shortest path, we'll start from the your last terminal, last destination. Better to say the vertex E in this example. So we are supposed to reach the vertex E, so it will be the last one. How we reach to A? How we reach to A? Let's just see in this step. The selection of E is through the vertex B. The selection of E is through the vertex of B. So the previous one should be B. Now let us see how we selected the vertex B. So vertex B is selected over here. Just see over here. So vertex B is selected through A. Vertex B is selected through A, and A is your initial vertex. So the task is done. The shortest path is we are supposed to move from A to B and B to E. A to B, the distance is given as 5, and B to E, the distance is given as 4. So this is the shortest path, and parallelly, the shortest distance is 5 plus 4, which is 9, and the same is from the last selection of E. From the last selection of E. So this is how we can find the shortest path. So in the graph, we are supposed to move from A to B and then B to E. And this is the shortest path by which we can move out from A and reach to the destination E. Okay, it looks quite easy when the graph is simple graph, and even though without a logarithm, we can do it manually. But the thing is that in real life, it's not like we do have this much simple graphs. The graph may be the complicated one. So we supposed to have some algorithm, and Dijkstra is one of those algorithm which solves such kind of graphs for the shortest path. So over here, we do have 3 points to be remembered or as a takeaway. First thing is what? If you see over here, in the first step, I did select the vertex D, and it is not in your shortest path. So the selection in these steps will not give you the guarantee to that vertex that it will include it in your shortest path. It will include it in your shortest path. This is one of the things. Second thing, we are supposed to select the minimum out of all uncrossed, unselected weights. Okay, once selection is done, then we'll see that what are the move out path. And when checking the move out path, will not visit a vertex again if it is already selected in the previous steps. Already selected. Okay, I'm saying selected. The third thing is what? the algorithm will not be terminated until unless all the all the vertices means those who involve in your selection, those who are involved in your selection. Here, all the vertices is not having the meaning that all the vertices of the graph. Here, all the vertices means what? Whatever the branches we do have, just see over here, these are the branches, okay? Either they should be selected or crossed. Once the task is done, a logarithm will terminate it, and to write the shortest path will start from the destination in the backward. So over here, we are supposed to arrive to the vertex E, and how the selection of E is done? Through the vertex B. So this is B. How the vertex B is selected? Through the vertex A. So the shortest path for this problem is A to B and B to E. I hope you understand the problem and as well as how we obtained the solution by using the Dijkstra's algorithm. Okay, let us take one more example so that you get more clarity on it. A little complicated one compared to the first example. So here we are supposed to travel from the vertex A to Z, and these are the different vertices which are there from A to Z in between. Okay, we'll use the same algorithm. So we'll start with the selection of initial vertex, which is A. The path from A to move out is A to B is there and A to C is there. So A to B, we do have 4 units and A to C, we do have 3 units. So total, this is 4 and this is 3. This is the step number 1. In step number 2, we are supposed to select minimum out of 4 and 3, which is 3. So now we have selected the vertex C with a weight of unit 3. Okay, now from C, let us see what are the ways to move out from C. So from C, we can move to B. Yes, B is there in the first step too, but still it is not selected. What I said, a vertex will not be visited again. A vertex will not be visited again if it is already selected. Okay, so here B is not selected, so we can visit B again. So A to B, it is given as 2 unit, sorry, C to B. Then we do have C to D, which is given as 3 unit, and we do have C to E, which is given as 6 unit. So total from C to B will be 3 plus 2, 5. This is 3 plus 3, 6. And this is 3 plus 6 is 9. Now in step number 3, we are supposed to select once again minimum from all unselected or uncrossed. So 4, 5, 6, 9. So we'll select the vertex B, which is there at a weight of 4 minimum. Now we'll cross the other, we will cross the other existing B having higher weight than 4. So this get crossed. Huh? This is the important point. Now we are on the vertex B. So ways to move out from B. B to C is there, but C is already visited in the previous step. So we'll visit from B to D. So only one path is there from B to D, having 5 weights. So the total will comes out as 9. This is the step number 3. Now repeat the step once again. So once again, the minimum one need to be selected, minimum from all unselected or uncrossed. So 6, 9, 9. Now over here, we do have 2 nines. So we can choose any of them. Okay, if they are minimum. Even though over here 9 is not minimum, 6 is minimum. Okay, if there is a tie between the minimum, we can select any one minimum. Tie between minimum may replicate that there exists more than one shortest path. So here I am selecting vertex D, which is having a minimum weight of 6 unit. Is there any other D having more than 6 weight? Yes, this is D, so this will got crossed out from here. The vertex with the same name having higher weight get crossed. Okay. Now on D, The ways to move out, we can move from D to F, having the weight of 5 unit. We can move D to E, having the weight of 1 unit. Can I move D to C? The answer is no, because C is already visited. Can I move D to B? No, because B is already visited in the third step. Will not visit once again if it is already selected. Now the total weight 6 plus 5 is 11 and 6 plus 1 is 7. Now repeat the process once again. Minimum selection out of unselected, uncrossed. So we do have this 9 as unselected, this 11 as unselected, this 7 as unselected. Minimum is 7. So we'll select the vertex E with a weight of 7 unit. Now let us check, is there any other E exist with higher weight than 7? Yes, this is there with 9. So crossed it. Okay, so this will get crossed out. Now we are on E vertex and let us see what are the ways to move out. So E to D is there, but D is already visited. E to C is there, but C is already visited. So we'll check it E to G. The weight is 5. This will make total as 12. Okay, once again the minimum weight. Till now, we didn't arrive at the destination, and also all the vertices which is there in these steps are not crossed or selected. So the minimum out of 11 and 12 is 11. So in this step, I will select the vertex F with a weight 11. Is there any other F with higher weight? So no, none vertex will be crossed in this step. From F, we do have one path. From F, we do have one path which is F to G, which is F to G. We can move F to G. Yes, F to G is also not selected till now. F to G is also not selected, is also not selected till now. So we'll see F to G and F to that step, which is what? G and G. The weight which is given is F to G. It is given as 2 units, and F to G it is given as F to G it is given as how much it is given as F to G 7 units. So this is given as 7. The sum will make it as 11 plus 7 is 18 and 11 plus 2 is equals to 13. So now the minimum from all unselected or uncrossed. So these are the vertices like 12, 18 weights. These are the weight which is neither selected nor crossed. So minimum is 12. I will select the vertex G with a weight of 12 units. Is there any other G having higher weight? The answer is yes. So cross that one. So we are on the vertex G with a weight of 12. The ways to move out from G is G to Z. This is having weight as 4. We can move G to F, but F is already visited, so will not visit it again. So this will make the total as to 16. 12 plus 4, 16. We arrive at the destination, but still there are vertices, there are weight, which is neither crossed nor selected. Okay, so let us select the minimum once again out of this 18 and 16. So quite obvious, 16 is the minimum one. Is there any other G having the weight more than 16? Yes, so this got crossed. Now we arrived at the destination, which is Z. And also, all the weights in these steps, if you observe, either crossed or selected, either crossed or selected. So that's how the algorithm will terminate or stop. So total how many steps we done? 1, 2, 3, 4, 5, 6, 7 steps. So algorithm is done. Now let us see how to write the shortest path. Okay, as already discussed in the last example, we'll start with the final destination, which is G. Let us see how the G is selected. It is selected in this step through the vertex G. How G was selected? How G was selected in this step through the vertex E, and how E was selected through this step by using the vertex D, and how D was selected. Where is D selection? Yes, in this step, it is selected through the vertex C, and how the C was selected. It is in the first step through A. So this is the shortest path for the given problem, that we should move out from A to C, C to D, D to E, E to G, and then G to Z. This is the shortest path. And what about the shortest distance? Either we can do the sum of all these edges weight, or the final selected vertices will give you the final weight. In this example, it comes out as 16 units. How to write it over there? Like in this graph, A to C is 3, C to D is 3, D to E is 1, E to G is 5, and G to Z is 4, which make it 16. 3 plus 3 is 6, 1 7, 7 5 12, 4 16. So this is how we can solve a problem based on the Dijkstra's algorithm. Hope you understand the procedure. So now let us close this session.